Okay. Good morning, everybody, and welcome back to Math 115. Hopefully, everybody had a restful weekend and ready to get back into the swing of some math. So, first thing to do is, well, first cast. So let me cast. So I was thinking about how I could make this kind of entire situation look better visually. And I'm kind of considering switching into this sort of dark mode of presentation, which I think looks a bit better. And also, I'm thinking that if you guys are doing like a lot of online class, this might be nice to not have to stare at like the white screen, but just have this nice kind of black screen. Does anybody feel strongly about switching to dark mode or not want to switch to dark mode? Okay, a couple students like it better. Okay, I think I'm going to roll with it for a while. The one thing I don't love about it is it kind of messes up my highlighting. Doesn't look quite as good, but that's okay. We'll get through it. Okay. So before we can move on to that, let me go back to last week, because what we were finishing up last time was just talking about some of these functions. So actually, really quickly, before we even start that, let me remind everyone that we have an exam on Thursday of this week. And I think it's what, the 4th? Probably the 4th. Yeah. Okay. And let's see, it covers up to 1.7. Okay, so we did A.1, 2, 3, 4. We skipped 8.5. We did 8.6 and 7, and then we did everything in chapter 1 up to 1.7, or we will have done all of that by tomorrow. And it'll go from, I guess I'll post it at 8:30 a.m. and it'll be due at 9 o'clock p.m. Okay, so that's not the usual 11:59 due date. Okay, so turn it in as a single PDF. You can print out the exam if you want and fill it out, or you can just fill out your answers on a blank sheet of paper if you don't have a printer. But what you will need to do is have some kind of scanning device for your work. So most people use their phone. If you don't have a camera phone, then let me know and we'll figure something out. Okay, so that's the exam. We still have a homework assignment due this Friday. Okay, so there's no gap just because we have the exam. We're just going to take the 2 days to do the review and the exam. So speaking of, we'll review on Wednesday. As with pretty much all the study materials that I'm going to provide you, this review is not really intended to be like the only way that you study for the exam. Hopefully you guys are studying at home, taking a look at the homeworks, looking at the ones that you thought were hard, doing some of the practice problems from the book, doing the practice exam, which, by the way, I'll post a video solution to the practice exam today, so you guys will have some time to review that. But I recommend that you try the practice exam on your own first. Okay, any questions about administrative things? Okay. Well then, let me go back and finish up what I was talking about last time. So last time I was just kind of giving you this, what we call this, quote, library of functions, okay? And we were just kind of going through all of these, and we want to know what all of these functions look like, because what we're going to talk about next is going to be function transformations. So when we look at function transformations, we want to understand how these graphs of these functions are going to change when we apply certain algebraic expressions or operations to them. Okay, so we're going to take all of these and we're going to transform them. We're going to, stretch them, shift them, reflect them, and do all sorts of business like that. Okay, so we had this function which is just a constant, will look like a horizontal line. We have this function just f of x equals x. It looks like a line with slope 1 and y-intercept 0. We did x squared. It should look like a parabola, right? We would take the point, 1, and we would square it and get 1, and then we take the point 2, and then we would get 1, 2, 3, 4, right? And then we take the point x equals 3, and then this would be the point 3 comma 9, and so on and so forth. And then we had x cubed, and we got to remember that if we're cubing a number, it's possible that when we cube a negative number, we will get a negative number. So that's why this one goes down in this direction. Okay. And on the right-hand side, it's a little bit steeper, because usually when we cube a number, if it's a bigger number than 1, we're going to rise faster than we are rising with x squared. So that was x cubed. We did the absolute value of x. Remember, the absolute value of x is just going to be equal to x if x is a positive number. So that's why the right-hand side just looks just like the graph of y equals x. And it's going to be equal to negative x if x is less than 0. Okay, so if x is less than 0, then we would take this number, which is -1, and we would make it positive by doing -1. So this point right here would be the point -1 comma 1. All right. Then we talked about the square root function, and one thing we have to remember when we're talking about the square root function is in order for it to be a function, we implicitly choose to only graph the positive square root, okay? So I might write it like this, where I just write f of x equals the square root of x, okay? And what you need to understand is I'm talking about the positive square root, since I didn't write a plus or minus sign. If I wrote a plus or minus sign, then I'm talking about both. But when I'm talking about this function, I'll just write it like this to refer to only the positive square root, okay? So it'll look something like this. It'll look like the top half of that parabola that, would extend like this if we had something like x equals y squared, right? Okay, but we don't graph that part because that would cause it to fail the vertical line test. All right, now let's talk about the cube root of x. Okay, so the cube root of x is going to look a lot like the square root of x on the right-hand side. And on the left-hand side, since we can do cube roots of negative numbers, in fact, we can do any odd-powered roots of negative numbers, we are actually going to graph. And if we do the cube root of something like -9, we'd get something like -3. So here's -9. And then this would be the point -9 comma cube root of -9. In other words, -3 comma -9 comma -3 is what it would be. Okay, then 1 divided by x. This is where I kind of had to speed up a little bit. So let me go back and talk more about this. When x becomes small, when we divide 1 by a really small number, you can practice this on your calculator. You divide 1 by like 0.00001. That's like doing 1 divided by 1 over 10,000, which would be like doing 1 times 10,000 over 1, which would be getting us 10,000. So when x gets really small, we see that 1 over x is big. Okay? So as x goes to 0 along this x-axis here, what's going to happen is our number is going to get larger and larger and larger. Okay? And as we go out to the right, what's happening is we're dividing 1 by some number which is getting really big, so we should expect it to be like, I don't know, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and so on and so forth, and getting really small. Okay, we're going to see the same exact thing on the left-hand side, except when we divide a positive number by a negative number, we get a negative number. Okay, and the size is going to stay the same. So the result of that is that we're going to see this graph is going to look symmetric about the origin. Okay, symmetric about the origin. Okay. Now the reason that 1 over x squared looks like this and it's symmetric about the y-axis instead of about the origin is because we have this x squared here, which means that when we take the negative numbers on the left-hand side and we square them, the denominator is actually going to be a positive number. So when we divide 1 by a positive number, we're going to get the same exact thing as what we would get on this right-hand side. Okay, so this one's going to be symmetric about the y-axis. Okay. So let's look at this one. F of x equals x to the power 3/2. Okay, and this is the first one that's kind of like really confusing, I think. But what does it say? It basically says we take the number x and we cube it, and then we take the square root. Okay, so first of all, we should make sure that we're only graphing on the positive side of the of the y-axis. So we should have only positive x values being plugged into here, because kind of no matter which way you slice it, if we plug a negative number and we cube, we'd get a negative number, then take the square root. We can't do that. Or we'd start with a negative number and square root it and then cube it. Well, we can't do the square root to begin with. So if we plug a negative number, no matter which one we do first, if we do the square root of x cubed or square root of x and then cube it, if we plug in a negative number, we're going to be doing the square root of a negative number either way. So we can't do the negative side. And what is it going to look like? Well, it's going to look a little bit like the right-hand side of x squared, except the growth rate is going to be a little bit slower than x squared. And why is that true? It's because 1.5, in other words, 3/2, is less than 2. Okay, we do bigger powers of numbers, we usually get bigger numbers, as long as the number that we're taking a power of is something larger than 1. Okay, so that's what that one's going to look like. And then we can do f of x equals x to the power 2/3. Well, this means we're going to square it and then take the cube root. Okay, so this one is going to be okay to do on both sides. We're going to get something which looks like a root function on the right-hand side, since this number 2/3 is less than 1. And then on the left-hand side, well, we would take a number and then square it, so we'd get something positive, and then take the cube root of it. We're going to get the same exact thing on the left-hand side. Okay, and then this last one is, we call this the floor function, and what it is for each interval here, it's gonna represent the, it's gonna be the number if we were to just cut off all the decimal points. So it looks like this. Okay, so for x equals 1.5, the floor function of 1.5 is going to be equal to 1. Okay, we take the largest integer which is less than 1.5. And then so on and so forth. That was 1, this was 2, this is 3. We go up to 3 and keep going like this, basically. Okay, that's what that one means. Okay, any questions about these ones that we just graphed? And this kind of finishing up these thoughts? All right. If not, here comes dark mode. And that just looks better, I think. If you don't like it, you can write me an anonymous comment on the Blackboard. Okay, so now we're going to talk about function transformations. So we're going to study how the graph of these functions, like the ones that we just drew in our library of functions, we're going to see how they change when we apply linear algebraic expressions. Okay, so let me talk about what a linear algebraic expression or operation looks like. Okay, that means we're either going to multiply by something. So we're going to do like a times f of x, or we'll do f of x times a, or we'll do f of x plus a, or f of x plus a, things like this. Okay, when I talk about linear algebraic operations, I'm talking about multiplying by a constant, either on the inside or the outside, or I'm talking about adding a constant, or subtracting one for that matter, on the inside or the outside. Okay, but we're not going to take powers, okay? We're not going to do stuff like f of x squared, okay? So just adding and multiplying basically is what I mean by linear algebraic operations. So for example, we could take something like this graph of f of x here, which I've drawn, and we can just add 4 to it, okay? So if we say that g of x is going to be equal to f of x plus 4, then we just say that the height of the function g of x is going to be the height of the function f of x, and then we're going to add 4 to it. So we should expect that graph to be shifted up by 4 units. Okay, so we just take the whole thing, copy and paste it, and move it up. That's all we're doing. Okay, so let's make that more concrete. We can talk about vertical shifts. Okay, so let's start first with just number 1. So we just take d to be some number, okay? So d is just the letter that I'm using to represent some number which is positive, okay? And then what do we say? We say that the graph of g of x equals f of x plus d. So if we take f of x and we add a positive number, then it's going to be, we're going to get the graph of the original function shifted up by d units. Okay, that's what this statement says. So as long as d is positive and we add it to f of x, that means we move up by d units. Okay? That's what that says. And then the secondary fact here is that if we subtract the positive number d, okay, so if instead of adding d, we subtract it, okay, then what we're going to get is the graph of y equals f of x shifted d units down. Okay, we already kind of saw what that looks like, but let's do some practice with this. So we'll graph the following functions. What we're going to do, f of x equals absolute value of x. So first of all, we know what that looks like. It's just going to come straight out of 0 with these lines like this. Now, that second line wasn't as steep, was it? There we go. That looks a bit better. So here's what the absolute value of x looks like. And here I can see that the number 3 is a positive number, and I'm adding it. So I should apply rule 1. Okay. Rule 1 said that the graph of g of x equals f of x plus d is the graph of y equals f of x shifted d units up, and here d is 3. So I'm going to go up 3 units, and I'm just going to redraw the graph. So it would look something like this. Yeah, I just shifted it 3 units up. Okay. So I just took the number 3 here, and I substituted for d in this equation, and I said, okay, the graph of g of x equals f of x plus 3 is the graph of y equals f of x shifted 3 units up. Okay. So now the second part asks us to do f of x minus 1. Well, I should use rule 2 since I'm subtracting a positive number, and I should just move the entire graph down 1 unit. That doesn't look quite parallel, does it? That looks a little bit better. So it's going to look something like this. Okay, so to get the first one, we just moved up by 3 units. And to get the second one, we just moved down by 1 unit. So that's how we do vertical shifts. Okay, similarly, we have horizontal shifts. Okay, and you don't necessarily have to write all of this stuff down if you have the idea down, but I'm going to read it out. So we take c larger than 0, okay, some positive number, again. We call it c this time instead of d. And what do we say? We say that the graph of g of x equals f of x minus c, okay, if we subtract c on the inside of the parentheses. Then what we're going to get is the graph of y equals f of x shifted c units to the right. Okay, and I put right in all caps here because some people, I mean, not some people, it's objectively confusing that the minus c corresponds to the right. We think we're going to the left, but that's not true, okay? Because we just think of the x-axis and we think, okay, well, if we have, 1, 2, 3, things which are less are to the left, okay? And this intuition is gonna mislead you here and make you think that when we do a minus, we should shift to the left. But when we have a minus, we need to shift to the right, okay? So you can memorize that, or what you can do is just rely on your intuition and remember that your intuition is going to make you think the opposite, and so you have to flip-flop when you have it on the inside. Okay? Okay, so we're going to shift to the right if we have x minus c on the inside. And likewise, if we have x plus c on the inside, then we're going to shift to the left. Again, going against our intuition, we think plus means go to the right, but plus actually means go to the left. Okay, so just remember, and this is generally true for pretty much everything, that when we put it on the inside, okay, it's gonna get wonky and do sort of the opposite of what we expect it to do. Okay, so keep that in mind as we go forward. So let's try graphing some horizontal shifts. We'll take this function f of x equals x cubed. Okay, so let's draw the original function. I don't know, looks something like this maybe. Okay. Now remember, I've got g of x here. It says f of x minus 2. So I take a positive number and I subtract it. Okay, so this is going to fall under category 1. And category 1 says, hey, if I subtract a positive number, I'm going to shift by that many units to the right. So all I'm going to do is take this whole thing and copy and paste it 2 units to the right. We moved 2 units to the right. And for h of x, well, I've got f of x plus 1. I'm adding 1 on the inside. My intuition's telling me that I should go to the right, but I know from the rules that we just learned that my intuition's wrong. I need to move to the left if I'm adding. So I'm going to move to the left by 1 unit. Okay, so 1 unit to the left. So that is how horizontal and vertical shifts work. So let me pause before I move on and talk about something a little bit more complicated and ask, are there questions about how we apply these vertical shifts and horizontal shifts? No, it's a little bit confusing that the horizontal one kind of seems wrong. Okay, well, if you do have questions, come to office hours right after class today. All right, so now we're going to talk about reflections. Okay. Let's just start with number 1. Okay. What does number 1 say? Okay. Just want to focus on just this one first. Okay, so say we take f of x and we just add a minus sign out front. Okay, we add a minus sign out front. Okay. Well, what is that going to do? That's going to be if we have y equals f of x. And this gives us the point x comma y. And we take g equals, we take some other line, y equals g of x equals negative f of x. Well, the point that's going to be on this graph is going to be the point x comma negative y, okay? We say that the height of the function g is going to be the negative or the negation of the height of the function f. Okay, so if f is 10 units tall, then g will be negative 10 units tall. Okay, or if f is negative 10 units tall, then g will be 10 units tall. Okay, so what this is going to do is it's going to move everything that is beneath the x-axis above the x-axis, and everything that was above the x-axis is going to go beneath the x-axis. Okay? So that's exactly what it means when we say that we reflect about the x-axis. Okay, so let me draw what I mean here. So say we have this function square root of x. I don't know, it looks something like that. I'm not going to bother getting really jiggy with this. Okay, and what's going to happen is if I take the negative of the square root of x, well, all I'm going to do is say that the height of g of x should be exactly negative of the height of g of x, or of f of x, excuse me. So it's going to be reflected across the x-axis, okay? So it looks like a mirror image, okay? So here we are in, like, you know, if you watch Stranger Things, this is the right side up, and this is the upside down. Okay? So that's what this negative sign is going to do. It's going to flip us into the mirror world. We're going to go beneath the x-axis. Okay? Or likewise, if we started in the upside down and we flip, then we're going to be in the right side up. Okay? Cool. So let's learn the second rule now. The second rule says the following. If we take that negative sign and instead of having it out front, which is what we did before, we're going to put it inside and we're going to attach it to that x there. Okay. Now, what is that going to do? What it's going to do, okay, is that if xy was on f, then negative xy is going to be on G. Okay, because we would take the point negative x, we would plug it in here, and then in here it would look like negative x. And so the height of G at the point negative x is going to be equal to the height of f at the point x. Hopefully that makes sense. In any case, if you don't feel like putting a whole lot of effort into having the intuition of why this is true, then you can memorize this rule, which says that if we take a negative on the inside, what's going to happen is we're going to reflect about the y-axis. What does that look like? Remember, the y-axis is this one that goes vertical. The x-axis is the horizontal. So it's going to flip into the, I don't know what you would even call this in Stranger Things, maybe the right side left. I don't care if you use this analogy or not, but you need to know how these graphs are going to change, and the effect of graphing the square root of negative x is that we're going to go to the left now, because what we do is we take the number, for example, -3, and what do? We take h of -3 is going to be equal to the square root of -3, which is going to be equal to the square root of 3. So we take this point here and we just move it over here. Okay? That's how we do those. See if I can get the reflections all on the same page. Okay. Any questions about reflections? Yeah, the second point. I can explain that again. Okay. So it's a little bit confusing. I understand. So basically what we're doing here is we're going to transform f of x into g, okay, by saying that g of x, the height of g of x at a point x, the height of g of x at a point x, so let me get rid of this negative x because I feel like that might have confused some people. The height of g at a given point x is going to be given by the height of f at the point -x. So if I want to draw G, so say I have F here. F looks like, I don't know, this. If I want to graph where the height of G of x is, okay, if I want to graph where the height of G of x is, and G of x is equal to F of -x, if I want to find out the height of G of x at this point x, okay, so how far up and down this asymptote, or this x value, how high should the function be? What this rule tells me to do is, okay, go over to -x and find out what is the height of f at this point. It's this distance here, okay? Then we take that distance and we copy it over and say that is going to be the height of g at this point. Okay, so that's how we do this process. Okay, we just copy over the height. Okay, so the height of the function g on the is just going to be the height of the function f at the point which is as far away from the origin as we are, but on the other side of the y-axis, okay? So this point here is going to get copied over here. This red, not red, let's use green. This green point right here is going to get copied over here, and so on and so forth. And so g of x is going to wind up looking like an exact mirror image of this. Wait. Hang on. This is not right. It should look like this. That, and then the top should look like this. There we go. Okay, so we flipped it across the y-axis. That's what we did here. Okay, if you want to see more about that, then stay after class and we'll talk about it. And if you can't come to office hours, then send me an email and we'll make an appointment, okay? All right, I want to make sure I can get to everything today. So we got stretching left, and that's it, pretty much. Okay, so what is stretching? All right, so now we're going to talk about the next algebraic expression. We already talked about doing pluses and minuses, and we talked about making things negative. And now we're going to talk about multiplying by a number. Okay, so this looks like word soup a little bit. Let me compress it. We have a is just some positive number again. Okay, you're noticing a theme here. We choose some positive number a, and we say the following: if a is a number which is bigger than 1, okay, if a is a number which is bigger than 1, and then we do g of x is equal to a times f of x, okay, then g of x, the graph of it is going to be stretched by a factor of a, okay? So in other words, if xy was a point on the graph of f of x, then x and a times y is going to be on the graph of g of x. Okay, so if x, some point on f of x is 5 units tall, we just multiply the height of any given point by this number a. Okay. Now, for the second fact, it's going to be if a is less than 1. Okay. If a is less than 1, then we call it a vertical compression, or we say that the graph is vertically compressed. Okay. And the same exact rule is going to be true for what we do to the height. Okay. All we do is we take the height and we multiply by the number a. If it happens to be a number which is larger than 1, then the height should be getting bigger, basically. And if the number is less than 1, then we multiply some number by something less than 1. It should be getting smaller. Okay, so let's see how this works in action. Oh yeah, and I'm going to show you guys by switching to Desmos real quick. So here's how we can see how this works. I think we were supposed to do y equals x squared. I thought I saved this before, but I guess I didn't. So here's the graph of y equals x squared. We can see as well how the graph of y equals, say, for example, 2x squared looks like. So what does it look like? It looks like we just took the whole thing as if it was on, like, I don't know, a piece of rubber. And we took our piece of rubber and we just stretched it vertically, and it distorted this image of this graph here to look like it is kind of taller and skinnier. Okay, it's like when you're manipulating images in like Microsoft Word and you accidentally stretch it only up, and like all of the proportions get out of whack and people look like they're 16 feet tall and stuff like that. Okay, it's gonna be that kind of stretching. Okay, and if we do the opposite, if we do something like y equals x squared, and let's now multiply this times a fraction. So something less than 1. Let's do 1/3. Oops, that should go over there. Then what does it do? It's like we did the opposite. We flattened the image a little bit, okay? So we flattened the image, and we moved everything down, okay? So the process here, I want you to imagine what's happening at this point 1, okay? So let's look at the point x equals 1. For our original graph, y equals x squared, we just take 1 and we square it and we get 1. So that's why the red curve passes through the point 1, 1. What the blue curve says to do is, okay, take x, then square it, and then multiply by 2, which is why the height of the blue curve, when we look at x equals 1, so we're just looking at this vertical line x equals 1. I'm sorry, I can't draw on the page. Wish I could like highlight. That would be cool. Oh well. If we look at the point x equals 1, the height of this blue graph is going to be twice the height of the red graph, and the height of the green graph is going to be 1/3 of the height of the red graph. Okay? And these things move kind of differently because at different points, okay, the height of the red graph will change. And that means that the distance between the red graph and the blue graph will change as well. For example, you can see that the distance between the red graph and the blue graph at x equals 1 is going to be exactly 2 units, whereas the distance between the red graph and the blue graph at x equals 2 is like 1, 2, 3, 4, 5, 6, 7, 8 units. Okay, so we're just vertically stretching here. That's what we're doing. Okay, so A is larger than 1, vertical stretch. A is less than 1, vertical compression. Okay. Now let's move on and talk about horizontal stretching and compression. So what do? Oh, we take some number, b again, which is going to be larger than 0. Definitely don't like that highlighting color. Take b larger than 0. Okay. And if b is bigger than 1, okay, if b is bigger than 1, and we multiply by b on the inside, okay, multiplying by b on the inside. Remember, everything on the inside has to do with horizontal stuff, okay? When we add a number on the inside, we get a horizontal shift. When we multiply by a number on the inside, we're going to get a horizontal stretch or compression, depending on if b is larger than 1 or less than 1. And again, the words that are going to go here are going to be the opposite of what they were with the vertical world. Okay, when we multiply by something larger than 1 on the inside, we end up with a horizontal compression. Okay, a horizontal compression, which is the sort of the reverse of what happened with our vertical stretches. Okay, when A was larger than 1 and we did a vertical stretch, we got a vertical stretch. Whereas if we do B is larger than 1 on the inside, we're going to get a horizontal compression. Okay. Likewise, if B is less than 1, then the graph is going to be horizontally stretched. Okay. And if you're keeping score, what this means is that if x comma y is on the graph of f of x, then 1 over b times x comma y is going to be on the graph of g of x. And that's going to kind of show you why when b is larger than 1, we actually get a compression, because this number, if b is larger than 1, this means that 1 over b times x is actually less than x was originally. Okay? That's what is going on there. Okay, so let's see the example with 1 over x. I'm not sure that's going to be such a good example, but let's see what it looks like. In fact, let's not use 1 over x. Let's use something like, oh, I don't know. Running out of ideas here. How about x cubed? Let's try just x cubed for the time being. And now what we want to do is try multiplying by some number on the inside. Is this what I want to do? Why don't I do like, yeah, we can do that, I guess. Okay, so if I multiply by some number on the inside, let's choose something which is larger than 1. So we'll just 2. Multiply by x, and then we just take that whole thing and cube it. Okay, this is what it means to multiply on the inside. Okay. Then the way that I can think about what I'm doing here is, since 2 is a large number which is larger than 1, I know it's going to represent a horizontal compression, and that's exactly what I see, right? If I take a look at the point 1, 1, which is on the purple graph, what's happened to it? It has been compressed to the left, where now we see that the point 1/2, 1 is on the graph of 2x to the power 3. Okay? So in this horizontal compression thing, what we're saying is that the distance between the purple curve and the y-axis is going to be remaining proportional to the distance between the black curve and the y-axis. Okay, so here we're compressing things to the left. Okay, so essentially if we were in Word, we'd be taking our picture and we'd be squeezing it inwards. Okay, squeezing it inwards from the left and right. Okay, we are compressing. And now we can try as well. We can do the parentheses and we can do something like 1/3. And we'll multiply that times x, and then we'll do the whole thing to the power 3. And as we expected, we wind up with a horizontal stretch. Okay, so when the number on the inside is less than 1, we actually get a stretch. Okay. There's just one last thing that I wanted to talk about today, and then we will be basically on track. That is the following. When we have multiple transformations going on all at once, okay, we have an order for how we do these. Okay, the order is as follows. Okay, so the first thing that we want to do is identify the parent function. Okay, so by parent function, I mean the function which is being transformed, such as those that were in our library of functions. And then we're going to do the following. Horizontal shifts, then we're going to do stretches and compressions, then we're going to do any reflections, and then we're going to do any vertical shifts we have. Okay, so in our last minute here, I'll do this example here. And we'll try doing this. So here we have a function f of x equals -2 times x minus 1 squared plus 3. This looks like a transformation of the parent function f of x equals x squared. So allow me to just do the shifts in order. I'll take my parent function. It looks like x squared. And the first thing I'm going to do is the horizontal shift, which says I should go 1 unit to the right. Okay. So then I can erase this stuff and I can redraw 1 unit to the right. So that was the first thing. Next, I should do any stretches and compressions, and I do have one. I'm multiplying by 2, so I should stretch by 2. So I'll redraw, and it'll look something like this. Stretch by 2. Now I should do any reflections that I have, and I do have a reflection. It should be across the x-axis. So I'll move it over to this side. I'm sorry, not across the x. Yeah, it should be across the x-axis. Sorry, it should be now going down like this. And then lastly, I'll do my vertical shift. So I'll move it 3 units up. So I'll count 1, 2, 3. That goes up to there. And I'll redraw, and it'll look like this. Okay, so that's kind of the process of how I would go through these transformations. And if you wanted, you could draw out a bunch of coordinate planes and do them all. Or you can try to kind of just imagine how it's going in your head and then draw the end results. Just make sure that you apply these all in order. Okay, so I'm sorry I went like 1 minute over. Class is over now. If you need to go, then go ahead. Otherwise, if you have questions, I'm here, and I'll have office hours until 10:30. So if you're wanting to study for the exam, then hang around. Anybody have questions on this stuff? All right, seems like maybe not. Okay, I'm gonna stop the recording then.